How's it going today? Today's going to be a shorter video, but we'll be taking a look at partial pressure and combined gases. Let's get started. Today we're going to start off by defining exactly what partial pressure is and why it is important, and then we'll look at how to actually calculate and use partial pressures to determine compositions of combined gases. For starters, let's talk about what partial pressure is. To do this, we also have to look at the way gases exist most of the time out in the world. Usually, there is more than one type of gas occupying the same space at the same time. The air around us, for instance, has nitrogen, oxygen, carbon dioxide, argon, and more. A lot of the time there is also water vapor in the air and a plethora of other gases. In situations like this, each gas applies its own pressure to its container, or in the case of air, it applies a portion of the air pressure that we feel. This pressure is only a part of the total pressure applied by all of the gases present, so we call it a partial pressure. You might be wondering why partial pressure matters. Simply put, partial pressure allows us to determine the composition of a gas or to calculate the mass of gases present in a sample. If you look at the various gas laws we have talked about so far, none of them take into account the size, mass, or kind of gas being measured, and they don't really need to. All gases behave basically the same. This can make determining something like composition very difficult, so using partial pressures can make this much easier. If you can measure the partial pressure, you can determine gas composition, and if you know the gas composition, you can determine the partial pressure. The best way to explain how to do this will be through some examples, but in words, partial pressure equals the total pressure times the percent composition. Let's take a look. This first example problem says the composition of dry air is 78% nitrogen, 21% oxygen, and 1% other trace gases. If the pressure of air at sea level is 101.32 kilopascals, what is the partial pressure of each component? So we're going to divide that up into nitrogen, which has a percentage of 0.78, so nitrogen. We're going to divide oxygen, which is 0.21, and other gases, which is 0.01. Other. And we want to determine the partial pressure of each one. So remember, the partial pressure, which I'm going to abbreviate as P sub n, is equal to the total pressure, P sub T, times its percent. In this case, that's 0.78, so times percent n. Right? Now, when we sub in our variables here, we get partial pressure of nitrogen equals the total pressure, which is 101.32, times its percent, which is 0.78, and that gives us about 79.03 kilopascals. So that's for nitrogen. Now for oxygen, we'll do pretty much the same thing, except it'll be PO equals PT times percent O. So in this case, that means that PO equals 101.32 times 0.21, to 0, sorry, and that is approximately equal to 21.28 kilopascals. And then lastly, for other gases, we're going to do P sub H. So P sub H equals P sub T times percent H, or in this case, P sub H equals 101.32 times 0.01, or about 1.01 kilopascals. Now we did some rounding, so it might not be exact, but if we add all three of these up, we should get our total pressure again. So we have 21.28 plus 1.01 plus 79.03, which gives us 101.32, which is exactly what we want to see. So all of the partial pressures, this oxygen, this is for the other gases, this is for nitrogen, add up to the total pressure. The second practice problem says a 10-liter container is filled with hydrogen gas and carbon dioxide gas. The partial pressure of hydrogen gas is 110 kilopascals. The partial pressure of carbon dioxide in the container is 140 kilopascals. How many liters of each gas are present? So, first things first, we've got our partial pressures, so we can determine our percent composition. We need the total pressure, and the total pressure we know is equal to the sum of all the partial pressures, so 110 plus 140 equals 250 is our total pressure. All right, so now we have our total pressure. We can start solving for the percentages of each one. So let's start with hydrogen, which is 110. So 110, the partial pressure of hydrogen, equals 250 times the percent that is hydrogen. And in order to solve that, we just need to divide both sides by 250, divided by 250. And what we end up with is that hydrogen equals 0.44, or about 44% hydrogen. Now we could go ahead and do the math for the other one. We could do 140 equals 250 times the percent of CO2, but we also know it's going to be 56% since the total add up to 100. So we know that CO2 equals 0.56. Now, this is the percentage composition in volume of the two. So this gas is 44% hydrogen and 56% carbon dioxide. That being said, we need to know how many liters, and we know that our total container is 10 liters. So if we have a total of 10 liters, and hydrogen makes up 0.44, or 44% of that, we will get that there are 4.4 liters of hydrogen. And if we do the same thing for our carbon dioxide, 0.56, we'll get that there are 5.6 liters of CO2. Okay, so those would be the two answers to that question. Let's review. When more than one type of gas is present in a container, each one exerts a partial pressure. All of the partial pressures of gases in a container must add up to the total pressure, and the partial pressure of one type of gas is equal to its percent composition times the total pressure from all of the gases. That's all for this video. Thanks for watching, and I'll see you next time.